Atoms are the tiny building blocks of everything we see around us. Imagine them like incredibly small Lego bricks that make up everything in the universe. These atoms are made up of even smaller particles called protons, neutrons, and electrons. Protons and neutrons reside in the nucleus, the atom's center. They give the atom its mass. Whizzing around the nucleus are the electrons, much lighter than their counterparts. Early scientists like Niels Bohr tried to understand how these electrons moved around the nucleus. Bohr proposed a model where electrons orbited the nucleus in fixed, circular paths, much like planets orbiting the sun. This model worked well for simple atoms like hydrogen, but failed to explain the behavior of more complex ones. Bohr's model, while groundbreaking, had its limitations. It couldn't accurately predict the energy levels of electrons in atoms with more than one electron. This was a major flaw, as most elements in the universe have multiple electrons. Furthermore, the model assumed that electrons followed fixed paths like tiny satellites. However, a revolutionary principle called the Heisenberg uncertainty principle challenged this notion. Werner Heisenberg proposed that we can never simultaneously know both the exact position and momentum of an electron. It's like trying to pinpoint the exact location and speed of a racing car at the same time. The very act of observing one affects the other. This principle shattered the deterministic view of the atom, suggesting that electron behavior was governed by probability and uncertainty. To better understand the atom, scientists turned to a new branch of physics, quantum mechanics. This theory revolutionized our understanding of the subatomic world. Unlike classical physics, which described objects as particles with definite positions and speeds, quantum mechanics introduced the mind-boggling concept of wave-particle duality. Imagine a beam of light. Sometimes it acts like a wave, spreading out like ripples in a pond. Other times it behaves like a stream of particles called photons, each carrying a specific amount of energy. This dual nature extends to electrons as well. They too exhibit both wave-like and particle-like properties, making their behavior difficult to comprehend using everyday experiences. Instead of fixed orbits, electrons occupy regions of space called orbitals. These orbitals are not like the well-defined paths of planets but rather represent the probability of finding an electron in a particular region. Think of it like a cloud. The denser the cloud, the higher the probability of finding the electron there. Each orbital is defined by a set of 4 quantum numbers, like an electron's unique address in the vast expanse of the atom. These quantum numbers dictate the energy, shape, and orientation of the electron's orbital. They govern how electrons are arranged within an atom, giving rise to the periodic trends we observe in the elements. This model successfully explains many properties of atoms and molecules, paving the way for advancements in fields like chemistry, materials, science, and electronics.